We're making the pancakes, and I don't want to talk too much, but here we use this controller that we wrote. It basically just opens about every container here. You see we were tipping with the fingertips against this because we had a good laser perception, but still this can be off by a centimeter or two. And by just using this tactile feedback of touching the handle before we grasp it, we have a pretty good estimate of where it is actually, and then we can just grasp it right away. Here you see how it's always just pulling somewhat in a direction, and this is using the compliance. So basically just pull and see where it goes. It will always follow the trajectory of smallest force. And then we are adjusting with the feeling of the fingertips, the orientation. These handles are very good for that, of course. We can feel how the center of the pressure in the fingertips changes when the handle and whether it's rotational or sliding. And problem you also saw that the base was moving during this. So often we run into the problem that we open some container and then we run into the limit of the robot's capability with the arm. And then of course we just move the base a little, and this is not very well integrated. You see it's first going like this a little and then with the arm. So this is not really nice so far, but it works. And this would be our idea of what to do first. So if we come into a kitchen, we just scan the whole kitchen with a laser, try to detect handles, and then pull and see what's going on. And then we would look into these containers and find out what's in there, and write that down in the semantic map again. So now we were also calculating a pose for the base. You see it's very restricted space there. So we had to calculate a pose, how we could find a place for the robot to execute this trajectory of getting out this bottle. And now we will just go along the trajectory that we had before to close the container again. So, I hope it's not, it's ran a little on camera, sometimes it's awesome. And yeah, this was not really intended, we are fighting with dynamics sometimes. And just as a warning, Willow Garage tries to make these robots very safe, and one point of this policy is that whenever something in the real-time system behaves strange, we just shut down the motors. So this happens about like once a day when we use the robot a lot. That some package from some EtherCAT controller comes like a few milliseconds late, and it's just dropping the plate on the ground. And I mean, this is just safety policy we can't get around, and I hope it's not happening. Usually it's not happening too often. But if you see that, you're warned. So it could happen that it just drops, and then you see it just going. And another thing I would like to say, different from Rosie, which has a lot of, high-end torque sensors in the joints. This robot uses springs to implement the compliance. So the arms are actually implemented with two gas-dent springs. So it can also get into some strange dynamic behavior. Of course, if you actually then the plate, hopefully with a pancake, to serve a fully robot-made pancake. So that's my colleague.
Thank you. Okay, so the first thing we're going to do is replace the pancake mix by live one, liquid. So, okay, so this is Rosie. I'm going to show it to you later. We're going to be repeating this demo, I hope, during the whole lunch. So if you are not in front, don't worry, you'll be able to see it again later.
So you're making pancake for everyone?
Well, we might run out of milk. But I hope everybody gets a piece. Okay, so this is Rosie, our robot. We have built it from scratch from discrete components. So as you see, we have the very nice Luca lightweight arms, and we have impedance control on these arms, active one, and also on the fingers. And we're going to start with the demo. So I'll be able to show you here what the robot actually sees, and for those who cannot see it, then I'll explain verbally. Okay, so green light, go. Okay, so we have a set of scripts, and I'm going to execute a plan to actually make pancakes. The first thing it's going to look for is for a pancake mix. And what you see here is the 3D view. So those are the 3D points. and it will plan a trajectory and move towards it. So this is recalculated every millisecond because we might push on the arms and might need to adjust if it's blocking against something. Okay. So right now it's gonna search on the table for a pancake maker. Okay, and we're gonna try to drop the mixture in the center. So this is vision right now. So the first one was using the time of flight camera, and this one is using the images to find a pancake maker. Okay, and now we'll see if we actually manage to make a pancake. Yeah, good. So that looks good. The robot uses the weight that it feels on its hand to decide how long it will pour. So for example, when the bottle is very empty, it's important that it flips more and waits a bit longer. Okay. And now what we're going to do is we're going to grab our spatula or our tool. Okay. And here we or by looking at further again. Now it looks a bit bigger. You see, we actually made a huge mount for it, and the reason is that these hands are about twice as big as human hands, and they don't have a 1 degree of freedom that we have with this one. And what the robot is doing right now is it looked at it, and it tried to get an idea of where the spatula is relative to its hand. Okay? And right now I will probably stick for a little bit.
22 seconds.
Okay, for 22 seconds, because we have told it that one side of the pancake needs around 90 seconds to cook. Okay? And now it's basically waiting. So hopefully next year we'll have 2 pancake makers, and then we'll have serial production of pancake. Okay. And now here comes the part where I hope everything works. So this is the tricky part for a robot, and that's flipping a pancake because it requires a certain dexterity. Okay, so we're gonna see. It should detect the collision with the pancake, which it did with the pancake maker. And now it leaves, and now it's gonna flip. Yes. And now we have to wait. This is the boring part of the demo because this part takes about 9 seconds. But in the meantime, the PR2 is already preparing the table, as you see over here, and it has brought cutlery. And the next thing it will do is put it down, and then when that pancake is ready, it will pick it up already over here. So yeah, if you have questions. And now comes the second difficult part for a robot. I don't know if we'll manage this time, so we have to hope. And that's actually getting the pancake off the surface. And this is difficult because right now everything is very slippery. And okay, we had a little problem. And before the here foot. So the difficult part is that once the pancake has cooked and everything is Teflon, you have to push it really quickly, and then the dynamics of the arm play an important role here. So we haven't gotten that perfectly right yet. So now the PR2 is using a circle detector to find the plate, and it will lift it.
So here's also the fingertips. I'm just waiting for the fingertips to touch, and you see it's very it takes very delicate touch.
I give back to Thomas.
You saw that it was just going to the plate until it touches. This is also what we humans do, I think. We only have we have pretty good vision, but it's just easier to go to the table and then move until we touch it. And these fingertips, they actually manage to tell me when I just have a very slight touch, and the dynamic is really like up to 150 Newton, which is the maximum force of the universe. That's all I wanted to say. Alex is no.
Okay, so, and now somebody will be lucky and will be able to eat robotic pancakes first.
Yeah. You look very hungry.
Because something that is different about this task in previous demos we used to show pick and place, but now we have a real-time constraint because the pancake burns if something doesn't work. Okay, so okay, work. Okay.
Okay.